Hello, and welcome to Agrosive Physics. Today is day 124, and what I'd like to do today is discuss electrical meters. Now, in a circuit, what we want to do is analyze the current and the voltage, or possibly the resistance, of the different components within the circuit. And when we do that, we're going to want to be able to check our results theoretically to the actual values. When we've been solving for circuit problems in our classroom and our lecture, we always assume that the wires have zero resistance. Now, of course, wires do have resistance, and the more we have in terms of the length of the wire, the more resistance there will be. So using a meter will allow us to see how close to the actual theoretical values our components have. For example, if we calculate the current flowing through a resistor to be 4 amps, how close to 4 amps is our value? Now, in order to find the current flowing through a component, we need to use what we call an ammeter. And an ammeter measures the amperage, or the amperes, or the current flowing through a specific component. Now, in order to connect an ammeter to a circuit, we need to break the circuit and put the ammeter in series with the component we're looking for. So if we want to find the current flowing through an entire circuit, we're going to place the ammeter in series with the battery. If we want to find the current flowing through a specific component, for example, resistor 1, 2, or 3, we're going to place it in series with resistor 1, 2, or 3. If it's a series circuit, we can place it anywhere. If it's a parallel circuit, we have to place it in the section where that component is located. Now, when we do that, we break the circuit and then rewire it as part of that section. Now, when we're measuring the variables or values of a specific component, for example, in this case, the current, we're going to want to have a situation where we don't change the values of the component. So we want the meter to be able to measure without affecting the circuit. So the way we do that is by setting the ammeter to have a very low resistance value. We take the ammeter and have the resistance as virtually zero, and then that won't change the value of the circuit itself. If we have a meter that affects the circuit, it's going to be irrelevant. It's not going to be useful at all. So we want to have an ammeter that has low resistance values, so we have a true value of the current. Now, on the other hand, we may want to find the voltage of a certain component. Now, remember, voltage is a fancy name for potential difference. So when we find the potential difference, we're going to want to find the potential at one point and compare it to the potential at another point. So, for example, if we're looking at the voltage across a resistor, we're going to want to place the meter on two ends of the resistor. So we're going to want to place one part of the voltmeter on one end of the resistor and the other end of the voltmeter on the other end of the resistor. If we want to find the voltage through the entire circuit, we're going to place it on both ends of the battery. If we want to find the voltage of a certain section, we're going to place it on two ends of that section of the circuit itself. Now, in order to avoid having electricity flowing through the voltmeter, we have a very high resistance value for the voltmeter to force the electrons to flow through the path of least resistance, which will be the circuit itself. So that means we connect voltmeters in parallel to the circuit. Now, ammeters are in series, voltmeters are in parallel. The ammeter has low resistance, voltmeter has high resistance. Now, if we're going to use a symbol to represent the ammeter or the voltmeter, we use a circle. And we draw a circle with a V for voltmeter or a circle with an A for an ammeter. V will measure voltage, A will measure amperes. Now, there also exists what we call multimeters, and that can do different jobs in a circuit. It can measure voltage, it can measure current, it can even measure resistance. Now, we've been discussing direct current in this section. That means the electrons are flowing in one direction through the circuit, and it's flowing either in conventional current from positive to negative, or the electron flow model, which is from negative to positive. Now, a multimeter can measure the voltage, the current, or the resistance in direct current circuits, like we would have in the lab, or it could even measure the voltage, the current, or the resistance in a alternating current situation. When you plug something into a wall socket, you're plugging it into alternating current. Alternating current means you have a sinusoidal effect on the voltage. The voltage oscillates between high and low from 0 to its peak value and then back to a negative. So it goes from positive to negative, and it looks like a sine graph. Direct current has a single value. When you connect a power supply to an outlet, that will take the alternating current and convert it to direct current. So if you're charging a laptop, or you're charging an iPad or a tablet or something like that, what you're doing is you're taking the alternating current and changing it to direct current, and then now you are charging the device you're looking for. Now, a multimeter has different settings, and what I have here is a multimeter that I use at home and I use in my lab itself. Right here we have different settings that we can use, and we can change what we're measuring from alternating voltage to direct voltage, direct current, and then resistance itself. You can even test whether or not you have continuity in a line by connecting the two terminals and seeing if you have a complete circuit. When you're wiring a house, you may have in the wall a spot where the wires have frayed and broken. And this will allow you to see if you need to open the wall and see if there's a break in the circuit. Now, in this case, I have my two ends here, which I can connect to either the outlet or I can connect to wires in a circuit and then see whether or not they are operating properly. If I'm in the lab, I'm going to want to undo the wires and then replace the meter if I'm using it as an ammeter. If I'm using it as a voltmeter, I'm just going to place the two prongs here and connect it to two ends of the resistance values. In lab, I like to use analog voltmeters and ammeters to show students how they're supposed to be connected in general. And if you're using, if you're doing electrical work at home, you would use a multimeter. Now, of course, electrical work at home should not be done by an amateur. Make sure that you have someone who is qualified to do electrical work, typically a trained electrician. Now, at this point, I'd like to do another complex circuit problem like we did yesterday, and we'll solve for different variables in the complex circuit, assuming that we have the light bulbs connected in different manners. Now, at this point, we'll take out the whiteboard and solve the sample problems now. Thank you. Being able to measure the voltage or current in a circuit is going to be important. And what we have are electrical meters in order to do so. We have an ammeter, which will measure current. And we have a voltmeter, which will measure voltage. Now, the way we denote those in a circuit is we use a circle with an A for an ammeter, or a circle with a V for a voltmeter. Now, the way they're connected matters. If we remember, an ammeter is measuring the current flow, so it needs to be part of the circuit. So the way we're going to connect that, and let's do this. We have this here. We'll do just a parallel circuit. If I want to know the current flowing through the battery, I can connect the ammeter up here. And we'll say R1, R2. If I want to know the current flowing through resistor 2, it has to be in line with resistor 2. Finally, if I want to find R1, I'm going to put it right here. So this one would figure out the total current, this one would figure out the current in R1, and this one would figure out the current in R2. So this is in series with the object you're trying to measure. Now, in order to avoid changing the circuit, because when you measure something, you don't want to affect its outcome, it has to have a low resistance. So R is low. Otherwise, it's going to change the total resistance. We'd have to use those values as part of the circuit, and then it changes the circuit's characteristics. Now, on the other hand, we have a voltmeter, which measures voltage. And remember, it's potential different. So it's connected in parallel. You have to have 2 points, and it finds the difference in voltage, which is why it's called potential difference. So you connect it as follows. What I'm going to do is connect a voltmeter here to measure the voltage in the entire circuit. If I want to find the voltage of R2, I would connect it like this. Now, you don't want electrons flowing through this voltmeter, or else that's going to change the value of this potential going through the resistor. So in order to do that, you need to set the parallel, and it has to have a resistance that is high. Now, if you connect the ammeter incorrectly, if you connect an ammeter here, because it has such low resistance, all the electrons are going to try to flow through it. So you'll end up breaking this meter. So it's important to connect the ammeter properly. This is one that's often broken. The fuses break quite often in the lab. So if you're going to connect something to measure the potential difference, you need 2 points, one before and one after the component. If you're measuring the current flow, you put it in line with the component, so you put it as part of the circuit. You need to break the circuit to put an ammeter in, and you need to just connect the two ends of the voltmeter to any point in the circuit to figure out the potential difference. So this one right here would find the potential across resistor R1. So that's the difference between an ammeter and a voltmeter. Ammeters are in series and voltmeters are in parallel. What we're going to do here is look at another complex circuit. And this one, we have a resistor in series. Then we have a junction, and we have 2 resistors connected in parallel. And just to mix it up, we're using a new power supply. It's variable, and I'm going to adjust it to 28 volts. So it's not a standard 12 or 120. Now, in order to solve this, we go to the furthest resistor, and we simplify it. And we work our way backwards to get our completely simplified equivalent circuit. Now, 12 and 24, how are they connected? Well, in parallel. So 1/12 plus 1 over 24 equals 1 over R. 12 to the negative 1 plus 24 to the negative 1 equals 0.125 to the negative 1 equals 8. So these 2 resistors combine to form an 8 ohm resistor. And then we continue the circuit. 6 ohms here. Well, 8 and 6 are connected in series. So 8 plus 6 is 14. So this is a 14 ohm equivalent resistance. So this goes to here. And we have 28 volts and 14 ohms. I'll get rid of our intermediate step here. And what we'll do is continue from here. 28 volts, 14 ohms, Ver. 28, I times 14. 28 divided by 14 should be 2. Let me verify. It is. So I is 2 amps here. And since these are equivalent circuits, we also have 2 amps flowing there. Now, at this point, we have 28 volts. 2 amps. Has to go through here. Then it's going to split up. So the 2 amps flows here, and then we don't know about the current there. But if we know the current and the resistance, we could do Ver. 2 amps times 6 ohms, and you get 12 volts. Now, 28, and you lost 12. How much is left to go through the other 2? Looks like 16 volts left. Now, these are connected in parallel. So if there's 16 volts at this point, all 16 has to be stolen here, and all 16 volts has to be stolen there, because there's no other components on the way back to the battery. So 16 divided by 12 gets me a current of 1.33 amps. And 16 divided by 24 gets me 0.667 amps. Now, if we think about it, let's verify. There was 2 going back to the battery, 1.33 going down, and 0.667 going in. What's 1.33 plus 0.667? Look at that, 2 amps. So we could always verify our answers at the very end. Now, since all the results are on this sporadically, I think it's important that when you're doing problems like this, you list resistors by name, and then you make a chart of usually VI and P. So voltage for R1. All right, if this is R1, R2, R3. Voltage for R1 was 12. Voltage for R2, 16. 16 for R3. Current for R1, 2 amps. Current for R2, 1.33 and 1.67. Now, power, you multiply across. 24 watts, 16 times 1.33, 21.3 watts, and 16 times 1.67, 26.72 watts. So if asked to see which one is the brightest, you'd say R3. If these were lamps, R2 is second, 1, 2, 3 in terms of brightness. But this allows us to find VI and P for every resistor on the board. Remember, R is going to be your constant, and V and I are going to change depending upon the situation. And that's the complex circuit.